So it's starting.
Okay, cool.
Can I record? Can you go to Facebook? Yeah. Check the feed. No, this is good.
Cool. That's great. Cool.
So I'll just close this right now, or
Might as well keep it running, yeah.
we'll see your face in this.
Faces and voices on the phone. Awesome. Thank you. Who else considering?
All right, we'll go ahead and get started. All right, good afternoon, everybody. Welcome to, I think it's the first Larry and EC seminar, joint seminar, unofficial yet, but we have a great speaker today. Dr. Song Lu is visiting us from University of Southern California, where he's currently a postdoctoral scholar. And prior to this, he was at City University in Hong Kong, where he did a postdoc and also completed a PhD degree in control engineering. And before that, he holds a PhD degree in control science from Chinese Academy of Science in Beijing. And his talk today is about MEMS and robotic manipulation at MEMS scale or precision scale, right?
Yeah.
So please welcome Dr. Liu, and let's get started.
Thank you. Thank you for showing up. Thank you for your hospitality, and thank you for having me. I'm Song. I'm a postdoc from the University of Southern California. My research focuses in robotic manipulation in precision scale, which is highly related to computer vision, artificial intelligence, and MEMS technology. I have the honor to be here at the University of Louisville to share my research with you guys. If you are interested, please feel free to contact me. Maybe we can come up with some good research ideas and do some awesome research work together. So through this presentation, I'm going to answer 4 questions. First, what is precision robotic manipulation? Second, what can precision robotic manipulation be used for? Third, what critical research problems I solve regarding precision robotic manipulation? And finally, where I'm going. So let's go to the first question. What is precision robotic manipulation? What are the characteristics? Well, precision robotic manipulation tackles the sensing, mirroring, tracking, controlling, and interacting problems in robotics field in micrometer level, which goes beyond the capacity of traditional robotics. Basically, it has 5 characteristics. First, the object size is in millimeter or sub-millimeter level, like the zebrafish embryo. Second, the motion resolution is 1 micron or 10 nanometers for translation, or 0.02 degrees for rotation. Third is the measurement accuracy is in micrometer or sub-micrometer level for precision, or 0.1 degrees for orientation. And finally, gravity no longer dominates physics. Interaction force is typically in millinewton or micronewton level. And finally, the gravity no longer dominates the physics. Instead, the capillary force and the electrostatic force become prominent. Yeah. So, what can precision robotic manipulation do for us? What are the potential applications? Well, The first application of my research in precision robotic manipulation is in nuclear industry for laser-based inertial confinement nuclear fusion. The four pictures here show the National Ignition Facility located in California for nuclear fusion research, which seems to be the ultimate solution for mankind's energy crisis. This target is the core part of the facility where the nuclear fusion reaction happens. And my work, I don't know anything about nuclear fusion. My work is to figure out some robotic approach to assemble this two-object device, which is actually half of this target. Well, the first step to assemble this device is to dispense high viscous glue onto the 16 blind holes sitting on the top surface of this aluminum object. The blind holes are 300 microns in diameter and 300 microns in depth. The difficulty of this work is we need to achieve 100 picoliter fluid dispensing accuracy in order to meet the target of precisely controlling the fluid dot attitude by an average less than 2 microns. This video shows the entire fluid dispensing approach we developed based on precision robotic manipulation. The second step to assemble this device is to fit this aluminum object and this silicon object together. The 16 claws on the silicon object should be well aligned to the 16 blind holes on the aluminum object. The final assembly area should be well controlled by 2 microns in precision and 0.1 degrees in orientation, so that the dispensed glue on the blind holes will form homogeneous contact with the 16 claws on the silicon object. This video shows we successfully assembled this two-object device by precision robotic manipulation. By the way, I developed the software and the hardware of this robotic system. Okay, this is the device before and after assembly, and here are the images taken from microscopes during different stages with the assembly process, which are before visual alignment, after visual alignment, and after assembly. And we have 3 microscopic cameras used here, the top view, the side view, and the front view. Well, the second application of my research in precision robotic manipulation is in aerospace field for the fabrication of traveling wave tube, which is widely used in video antenna systems. A traveling wave tube magnifies the power of electromagnetic waves. It has a helix structure in the center, surrounded by 3 pillars. And the first step to fabricate such a traveling wave tube is to fabricate this helix structure by precisely controlling the helix angle. And this is the robotic system we developed for the fabrication of the helix structure. This rotation stage will actively rotate this rod, and this translation stage will passively feed the metal wire onto the rod in order to form the helix structure. 2 lateral microscopes are used to feed back visual information, while a force sensor here is used to feed back the tensile force along the metal wire. During the wire wrapping process, during the fabrication process, this rod is kept rotating strictly upward by differential kinematics-based forward feed control and the visual backward feed control. And during the wire wrapping process, the tensile force along the metal wire and the relative pulse between the wire and the rod should be well controlled. So it's hybrid force and precision control for this wire wrapping process. The 2 images here are taken from the microscopes during the fabrication process, and this is the final fabricated helix structure. we will control the Higgs angle with a standard deviation of 1.5 degrees. Once we fabricated the traveling wave tube, we need further to put it into a cylinder. As you can see, there are 3 grooves in the inner wall of the cylinder. So the 2 objects here should be well aligned in 3D space in advance before assembly. We proposed a course to find orientation alignment scheme followed by precision alignment. The technical problem concerned here is actually a visual problem to extract invisible features from microscopes. As you can see that this cylinder is a symmetrical structure. From the lateral view, the center line of the cylinder is exactly the middle line of the 2 started edges of this cylinder. But for this traveling wave tube, it's asymmetrical. From the lateral view, the center line of this traveling wave tube may not coincide with the middle line of the 2 started edges. I proposed a method to solve this problem, and I will cover this method later in the technical contents. Another application of my research is in bioengineering for in situ dexterous particle rotation. Typically, in bioengineering, people use optical tweezers to manipulate particles or cells. Focused laser, like this, can generate a kind of a trapping force to hold the particles or cells. And optical tweezers can hardly rotate particles. So I developed a robotic approach based on 2 soft probes for in situ dexterous particle rotation. The probe we used here has a slender geometry with the diameter decreasing asymptotically to be as small as 1 micron. So the probe is very flexible. We measured the stiffness of the probe under SEM, and the stiffness of the probe can be as small as 3 Newton per meter, which is actually comparable to the stiffness of the micro cantilever within the SEM. And we use the lateral edges of the probes to grip the particles. Here shows in situ flip rotation and the lateral rotation of a spherical target. With the capacity of flip rotation and the lateral rotation, we can actually rotate the particle into any direction we want. The novelty of this work is, for the first time, we achieved large-scale particle rotation based on only 2 soft fingers. And the second novelty is, for the first time, we achieved large-scale particle rotation about 2 independent axes. So far, I discussed the applications of my research in bioengineering, in nuclear industry, and in aerospace field. We can also find other potential applications of precision robotic manipulation in advanced manufacturing, in biomedicine, and in IT industry. All these applications highlight the significance of the research in precision robotic manipulation. And now let's go to the 3rd question. What critical research problems I solved regarding this field? Well, research in this field is quite interdisciplinary, which is highly related to mechatronics, control theory, and electronics, etc. My research efforts were mainly put into the computer vision, artificial intelligence, and MEMS technology related problems. Let's first go to the technical contents of my research regarding robotic vision. Microscope is indispensable and widely used in precision robotic manipulation. A single microscope suffers from limited depth of field, typically ranging from tens of microns to a few hundred microns. So people usually use multiple microscopes, as the one in our lab, for precision robotic manipulation in 3D space. Here, our uniqueness here is we use the image Jacobian matrix to organize the information from multiple microscopes. This image Jacobian matrix maps the image space to the physical motion space, which actually establishes the hand-eye relationship for a microrobot. And the advantage of this image Jacobian matrix is it's constant instead of robot state dependent. And in addition, it's tailorable, which means we can customize this matrix according to the features from each specific microscope. Let's take this top view microscope as an example. This is the image Jacobian matrix, which by definition should satisfy this formula. And based on this formula, we can do physical measurement in 2D plane. Supposing we would like to measure the physical distance between the two circles from this image. Once we extract the circle center coordinates from this image, we can calculate this 3-element vector by the pseudo-inverse of the image Jacobian matrix. And then we can calculate the physical distance between the two circles by the square sum of the 3 elements in this vector. It's quite simple for 2D measurement. By the way, torus images are quite common in applications like the cell identification, and I developed an algorithm for circle extraction on this kind of images. The algorithm will first downsample the original image to find some candidate points inside the circles. And then, using the candidate points as reference points, the algorithm will scan the image to find out and cluster the circle edge points. And finally, the algorithm will fit the circle edge points into circle parameters, including the radius and the circle center coordinates based on Rensec method. This proposed method outperforms the most widely used circle extraction algorithm, PPHT, in both execution time and accuracy. And here, the PPHT stands for progressive probabilistic half transform. We discussed visual measurement in 2D plane. Here is an application concerning visual measurement in 3D space. Passive compliance is widely used in traditional robotic manipulation, which enables the robot to be more compliant when interacting with the environment. And the remote center compliance, also called ICC, is a typically used passive compliant device in robotics. Regarding precision robotic manipulation, we can simply use a coil spring and passive compliance to assist the manipulation task. And here in this application, we use a 1.5 millimeter in diameter coil spring to assist the precision pegging hole assembly task. This coil spring can be deformed in 3D space by lateral transverse deformation, vertical compression deformation, and bending deformation. Different kinds of deformation correspond to different kinds of interaction status between the objects. So if we can differentiate each kind of deformation of the coil spring, we can better understand the interaction status between the objects for more reasonable motion planning of the robot. In this application, we use 2 lateral microscopes to measure the 3D deformation of the coil spring. Taking measurement of the 3D transverse deformation as an example here, GF and GS are the image Jacobian matrix of the front view and the side view, respectively. And once the 2D projections of the 3D transverse deformation the two microscopes are extracted, we can calculate this 3D transfer deformation by this formula. This table shows some experimental results regarding the 3D deformation measurement based on image Jacobian matrix. As you can see, for compression and transverse deformation, we achieved 2 micron measurement accuracy. And for bending deformation, we achieved 0.1 degrees measurement accuracy. Yes. We successfully applied this technique to assist precision packaging whole assembly, and in this task, we deliberately misaligned the objects by 0.5 degrees, and we still successfully fit them together. This means by visually supervising the passive compliance, precision robotic manipulation is more tolerant, more compatible to the visual measurement, visual misalignment errors. This is the big contribution to the precision robotic manipulation field. I published this method in the IEEE Transactions on Mechatronics, and here is the comment from manual reviewers. This is the new control system for precision robotic manipulation tasks. Here is the invisible feature extraction problem we ever mentioned in the fabrication process of traveling wheel tube. The invisible features, like these 2 lines here, which are actually the projections of the 2 corner points from the top view, can actually be determined by the view direction vector between the microscopes. And the view direction between the top view and the side view can actually be calculated, be determined by the image Jacobian matrix. Supposing this image Jacobian matrix belongs to the side view, and this is the top view image Jacobian matrix, then for the top view microscope, the cross product of the 2 lines of this image Jacobian matrix will yield the optical axis vector of the side view. And then we multiply this optical axis vector to the image Jacobian matrix of another, the top view microscope will yield this view direction vector, which is the view direction vector of the side view with respect to the top view. This calculation process is very simple and accurate. I'm the first to propose this calculation theory for the view direction vector calculation. And accurate visual measurement in 3D space also endorses us with the capacity of accurate visual force measurement. This is kind of a straightforward. Taking this flexible micro probe as an example, we can calculate the bending stiffness of this probe. We can measure the bending displacement of the probe from microscope. We can therefore calculate the bending force from this probe exerted on the target. With this technique, we can achieve high precision force measurement in micronewton level. Despite all these advantages of a microscope suffers from limited depth of field. So it's pretty hard for microscope to track the 3D motion of particles or whatever targets. The technical problem concerned here is we need one-shot autofocusing instead of autofocusing based on sequential images. I proposed a method to solve this tracking problem for binocular microscopic vision system. As you can see here by this right side image, the object edge becomes more and more blurred as the defocusing getting worse. The proposed method basically comprises 2 parts. The first part is to estimate the defocusing of the microscope based on Bayesian inference theory from one single image. The second part is to predict the motion state of the particles based on Kalman filtering. This framework, this tracking framework works well for both particle angular motion and particle translation motion. And we achieved sub-pixel visual tracking accuracy for angular velocity less than 0.75 pi and for translation velocity less than 3,000 microns per second. For your clarity, here shows the performance of the proposed 3D tracking algorithm for binocular microscopic vision system. Compared with the reference method, as you can see, the tracking trajectory, the blue line is the truth trajectory, and the red line is the tracked trajectory. The tracking trajectory is much more smoother, which means the tracking precision, the tracking accuracy is much more better. So far, I briefly introduced the technical contents of my research regarding robotic vision. I listed 5 points here. Each point has been successfully applied to practical applications to solve practical problems, including the visual measurement problem, for control problem, and for tracking problem. And each point here has also got well acknowledged by peer-reviewed journal papers. I also put some efforts into robotic learning, and in precision robotic manipulation, the objects are typically very fragile. I think we all here have the same feeling, right? Like this 400 micron thick silicon object. So people in precision robotic manipulation typically use conservative control strategy to manipulate the objects in order to protect the object from breakage. Here shows the force trajectory and the motion trajectory during the fitting process of the two objects here under conservative control strategy. As you can see, we need almost 120 control steps to go through the entire fitting process, which is just 400 microns thick. And this is really low efficient. To better improve the manipulation efficiency, I developed a robotic learning model. This model is described by the 5 tuple, including the robot state set, robot action set, the probabilistic state transition function to describe the fitting dynamics between the objects, the rewarding function to evaluate the performance of the learned state transition function, and this kind of factor for control purpose. And this state transition function is well proved to follow the Gaussian form. And we would like the robot to learn the spatial stiffness matrix and the state covariance matrix by the robot itself. With this probabilistic robotic learning model, we developed an n-step motion planning scheme which can forecast the future by n steps further. As the motion planning step goes further, the confidence on future state becomes weaker and weaker because we will prove that the state covariance matrix becomes linearly larger. And we will evaluate the performance of the entire control strategy by a confidence factor and use this confidence factor for future motion planning. Here shows the performance of the proposed robotic learning model. compared with conservative control strategy, the manipulation efficiency was largely improved from more than 120 control steps to less than 20 control steps. In addition, both the force trajectory and the motion trajectory become much more smoother. Even under alignment errors, this proposed robotic learning model still works in higher efficiency. I used a similar approach to solve the problem of simultaneous interaction of multiple agents. Here we have 3 objects, and we would like to fit them together. This is the governing equation of the 3-object interacting process. As you can see from this equation, we cannot figure out the interaction status between each 2 objects from the governing equation directly. The robotic learning model here provides us a probabilistic solution to this problem. First, from the governing equation, we can get a hyperline. It's the general solution to this governing equation. We can get this hyperline to represent the solutions to this governing equation in a 9-dimensional space. And from the robotic learning model, we can get 3 Gaussian balls to represent the probabilistic distribution of each state in a 3-dimensional force space. And we will prove that the probabilistic expectation of the state equals the specific state with the largest probability. And this specific state can be well formulated by the learned model parameters. We also defined a confidence factor to evaluate the performance of the learned robotic learning model. If the model works well, which means we get a large confidence factor, we will move forward the interaction process. If we get a relatively lower confidence factor, we will withdraw the action and deploy a relatively conservative action. If at the worst circumstance, the robotic learning model failed to describe the fitting process, the interaction process, we will withdraw the action and deploy the most conservative control strategy, by which we will move the agents one by one instead of a simultaneous interaction. With this method, we successfully assembled a 3-object device. The action withdrawal rate is less than 5%, which validated the effectiveness of the proposed robotic learning model to solve the problem of simultaneous interaction. In the following is my research regarding MEMS technology and AI. Here is MEMS resonant microphone array. Resonant microphone works at the resonant frequency from where we can get much higher sensitivity compared with flatband microphone. Due to the array design, we can customize the MEMS resonant microphone array for dedicated frequencies for specific applications. By far, we have successfully fabricated MEMS resonant microphone array by a cantilever design and spiral structure design. This is the MEMS fabrication process of the MEMS resonant microphone array. It is very typical, so I would like to go through this slide. The first application of MEMS resonant microphone array is for abnormal respiratory sound detection. Wheezing is the typical symptom of asthma attack. And in a frequency domain, wheezing has several characterizing frequencies. And we customized a resonant microphone array based on these carried routing frequencies for better Within classification or Within detection. And here shows the sensitivity of each specific microphone within the array. The MEMS resonant microphone array will inspect the lines sound from multiple channels. And the signals from the different channels are fed into a 10-channel, 12-layer temporal convolutional neural networks to learn a 10-dimensional feature vector. And then this feature vector is classified by a logistic classifier for Within classification. This framework combines the MEMS technology and deep learning, achieves 97% Within classification accuracy, which highly outperforms the state-of-the-art approach, which is less than 90%. The second application of MEMS resonant microphone array is for active noise cancellation or hearing aid. In this application, the microphone array will inspect the sound, find out the noise, and speak out the noise through a speaker, but in opposite phase. The played sound will interfere with the environment to cancel the noise part before going into the ear. The technical content here is we use a single channel 11-layer TCN. TCN is short for temporal convolutional neural networks to track the signals in 90 milliseconds history to find out the noise intensity at the current time in order to cancel the noise. Here shows the performance of the framework for active noise cancellation combining MEMS technology and deep learning. And we tested this framework over pattern noise and white noise. For pattern noise means the noise is constructed by several random frequencies. We achieved 92% active noise cancellation performance. And this is the noise before and after cancellation. Yeah, this is in the time domain. And for the white noise, we canceled 5%. For your reference, the state-of-the-art analog active noise cancellation approach can only cancel 50% white noise in terms of noise energy. Yes, energy. Yeah. Apart from sensors, we also use MEMS technology to fabricate transducers. Here is a self-focusing acoustic transducer, which has a PDT plate in the bottom, covered by the thin PDMS layer. The blue line and the blue line is the electrode, and the red line, the red line is the UV cuticle adhesive. This thin PDMS layer works as Fresnel lens to focus the acoustic field into a single focal point, where we can get a very high focal pressure. This is the front side and back side of this transducer. We tested the focal pressure with the hydrophone, and this is the pressure distribution near the focal point. As you can see, we get the predominant focal pressure, and the focal pressure can be as large as 1.1 megapascal. And we successfully tested this transducer to eject water droplet. Can you see this water droplet? And potential implications of such a transducer in robotics is for non-contact manipulation of particles or small objects. I will show this video. And in this place, there is embryo. It's a zebrafish embryo. So till now, I introduced the technical contents of my research regarding robotic learning, robotic command, sensors, actuators, and artificial intelligence. This working experience covers most of the key research areas in robotics and lays solid foundation for my future research works as an independent researcher. So where am I going? Now I will briefly introduce my future research plan. My first future research plan is for robotic cell membrane transplantation. I already discussed this with a doctor in neuroscience, and I confirmed that cell membrane transplantation is theoretically feasible, and it has great application potentials in neuroscience to treat neural disorders. Technically, cell membrane transplantation is kind of like the patch clamp technology. We will first localize some part of the cell membrane, which may contain some ion channels, and then peel off the membrane slice, and finally put the membrane slice into the membrane of another cell. It's very simple, right? But it's very difficult. From the robotic perspective, we need to figure out the grasping, targeting, slicing, and releasing of a cell membrane slice. I have gained enough working experience for the grasping and the targeting, and I still need to put further efforts to understand the dynamics of the cell membrane for slicing and releasing. The second future research plan is wearable soft rehabilitation robot. The rehabilitation robots have been prosperous in recent years, and I'd like to put efforts in this field from a new point of view by combining the MEMS technology, cross-modality learning, and deep reinforcement learning. This way, I think we can get a new insight for the rehabilitation. I have done some preliminary work for this future plan, and this is one of my ongoing projects in USA regarding this soft 3D force sensor. This force sensor has the silicon base covered by the thin PMS layer. There is a group of continuous structures in the silicon base. This force sensor is expected to detect the normal force and the shear force simultaneously. So it's 3D force sensor, and based on this force sensor, we can organize kind of soft force sensor networks to get data for rehabilitation analysis. And this is the commercial simulation of this 3D force sensor under 3D force. I also have several other future plans, like the vision guided robotic learning by demonstration, or visual and verbal guided robotic learning. These future research plans are formed from my research background and their potential to apply funding support. Here are the potential funding sources from NIH and NSF. Most of the programs are dedicated for early-stage faculty members, like this CRII. Yes. And I think a successful application of these programs will help to establish the research reputation for my early-stage faculty career. Finally, I have established strong cooperation relationship with the robotics research labs worldwide, like from the United States, from Germany, from Hong Kong, from Canada. This is Dr. Sun's lab, and from China. This robotics research labs will also provide technical support for my future plans. So this is my presentation. Thank you for your time. Thank you for your patience. Thank you for having me.
All right, thank you very much. I'll open to questions.
Yeah, I welcome.
All right.
Please go ahead.
What kind of systems did you use to do the manipulation? We saw a lot of what was happening under the cameras, but what's making it go?
Okay, the system is, let me show you the system. Oh, I'm sorry. So this is the robotic system we This is the system. Okay. I'm sorry. Yeah, I built a automatic robotic system like the one in Dr. Porter's lab. This robotic system has 3 microscopes with the working speed from 3 directions, and I also have a manipulation stage, yeah, which has 3 rotation degree of freedoms, and 2 or 3 manipulators. Yeah, actually the same as yes.
Take a look in there.
Thank you for your question. Please go ahead.
I actually have a question related to that. You had system for the fluid dispensation on a level of a few hundred picoliters, fluid dispensation. So what kind of system did you use? Was it a custom made or you have purchased it? Was it off-the-shelf system for the fluid dispensation?
You mean how I achieve picoliter fluid?
Yes, exactly.
Let me change this page. Thank you for your question. Okay. We have a point laser sensor, point laser range sensor, which is very precise. And this point sensor is actually equipped with this top view microscope. And we will use the visual information to guide the laser sensor to measure the depth of the banana holes and to measure the full dot attitude or the height. And we also use this dot laser sensor to scan this area to calculate the entire volume of the fluid dispense. So, and this accuracy is practical measure accuracy, yes, by the dot laser sensor.
So I have a question about your the 3-camera Jacobian image processing system.
Okay.
What is the workspace of this system?
Working space.
Yes, working space.
You mean the dimension?
Yeah. I mean, how
large?
large you can automatically track under these microscopes?
Okay. Thank you for your question. Let me. Oh, this is our system. This picture. You can say we have 3 microscopes here: the top view, 2 lateral views. For the 2 lateral views, there are precision on 2 motion stages, and the motion stage can move along the optical axis direction. So, under such configuration, the working space is typically 3 centimeter by 3 centimeter by 3 centimeter in dimension. And if we want to extend the dimension, we need to place this microscope in motion stage slippage with 3 translation degree of freedoms. That way we can expand the working space.
Yes. So that leads to another question: is how do you handle that's all of your workspace. For example, you have to feed some small particles into your space, how you handle it.
Yes, the here is if the object moves out of the field of the microscope, it will cause a singularity problem of the visual sorting system. Based on our image matrix, let me take the page first. Based on this image matrix, we can precisely predict where the object is going, neither in the 3D space and in the image space. So we can effectively prevent the objects from being moved out of the field. Yeah. So in my applications, there is no such problem. Yes. Thank you for the question.
All right, so I have a question.
Oh, please.
So typically you have these cameras, right, from the top
Top?
and then the sides.
Yeah.
So my question is, in your image Jacobian formulation, seems to me it's possible to look at where to place the cameras to get the best conditioning of that matrix for pseudo-inverse maybe, to enhance your precision
Okay.
of measurement. Have you thought about that? At which angles to actually optimally place the cameras?
Okay. Our image matrix under this definition has no requirement on the configuration of these microscopic visual systems. Actually, they can be placed on any angle. Yes. Thus, it is calibrated. It's constant. So we don't require the system to be, for example, to be strictly precision charger. We don't have such regulation requirement.
I guess my question is there a configuration which will give you the best numerical conditioning of that matrix?
I don't give a thought on that. Probably not, I think.
I mean, I think that's interesting.
Oh, thank you, thank you. Before we propose this method, people in precision robotic manipulation, they typically require very strict hardware regulation over the view angle of the microscopes, because we don't know, we cannot reconstruct the 3D position of the object if we don't know the relative position between the three microscopes. And with this image matrix, we actually convert all the problems into this manipulator space. All these things, all these positions, angles can be represented in this manipulator coordinate space. So it's quite simple for our research. Yeah, and it's effective. Thank you for the question.
All right, thank you.
I have a question. So in one of the slides, you showed the optical trapping.
What?
Optical trapping.
Great. Okay.
Tweezer. Optical tweezer.
Okay.
So you basically rotated the bead and then measured the bending stiffness and force.
You mean
here.
This one?
Yeah, this one or the next one here.
Okay.
So you are measuring the bending stiffness and then finally the force.
Yeah.
Now the displacement, bending stiffness, and force, they're all interrelated.
Yes, of course.
Now, before doing the experiment, which information you had? Because if you don't know the bending stiffness and if you don't know the force, you can only get the displacement information from the imaging. How did you
That's a good question. Yes. Actually, we established a mathematical model for this probe to calculate the bending stiffness according to the diameter of each specific position, which means contact with the target. So we have a theory, we have a formula to calculate the stiffness. That's the first point. The second point is, in this model, we have several parameters, and we use SEM. In SEM, we have a micro cantilever, and the stiffness of the micro cantilever is known in advance. So we can measure the force by the SEM, right?
Okay.
So with the help of SEM, we calibrate our equation. So in practical applications, we just need to know the diameter of the probe in the contact point,
Okay.
and then we can calculate the bending stiffness.
It's still not clear. So you are saying you already calibrated the cantilever using SEM. Then what are you doing in the optical trapping?
No. The cantilever is within the SEM.
Okay.
This micro cantilever is some part of the SEM. And we use this cantilever within the SEM to calibrate the equations, the formulas,
Okay.
to represent the stiffness of this probe. We have a theory to calculate the stiffness.
Okay. Now it's clear. Okay. Thank you.
Thank you. Thank you for the question.
All right, any other questions?
All right, well, let's thank our speaker then. Our speaker will be here for a while to talk to you. If you want to hang out and ask some questions in private, you're welcome to. Thanks for coming. Otherwise, we'll see you next time.